Hello everyone, I am Shayok Kumar Dhar. Now I am going to solve a very beautiful problem on ring theory that came on CSIR NET. It's basically very important for NET, GATE, NBHM, TIFR or this type of exams. Okay, it has been said that RB a finite non-zero commutative ring with unity, then which of the following are necessarily true? First option told that any non-zero element in R is either unit or a zero divisor. The second option is just negation of the first element. Due to the problems for spaces, I didn't write it. Okay. So for the first option, let R be a non-zero commutative non-zero finite CRU. Okay, I am taking R like this. Okay, since it is finite, I can write it like this. I can easily write it like this. Okay, now let A, which is not equals to 0, belongs to R. I am taking an non-zero element from R. Okay, let A is not zero divisor. I am taking A not to be zero divisor. Okay, so I will prove that. I want to prove that then A is a unit. If option A is true, then I have to prove that A is a unit. Let's see if I can prove it or not. Okay, now if A into AI equals to 0 for some AI belongs to R, if this happen, what does it imply? It implies that AI equals to 0. Why? What is the reason behind it? Because A is divisor of 0. That's why product of two non-zero element, it is two non-zero element under multiplication cannot give you 0. Okay, so AI forcefully to be 0. Now if AI not equals to 0, if AI not equals to 0, it will imply that A1, A2, A3, An, all are not equals to 0. Okay. So if AI not equals to 0 for I equals to 1 to n, that implies that A1, A2, An all are not equals to 0. Okay, from the previous one, because if those are if this product is 0, then AI must be 0. So contrapositive, if AI not equals to 0, then this multiplication not be 0. Okay, I have written this only. Okay, and also if AAI equals to AJ for some I comma j, it will imply that AAI minus AJ equals to 0. If I take A common, then AI minus AJ equals to 0. And from this, again, AI minus AJ equals to 0. What is the reason? Because A is not divisor of 0, not 0 divisor. So, it means AI equals to AJ. But I have taken that these are the distinct elements. These A1, A2, A3, all are distinct elements of R. So these two elements can't be equal. So this implies that A1, A2, A3 dot 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 AN are distinct elements of R. All are distinct elements of R. Okay, so there are n distinct elements and none of them are equals to 0. So these elements are basically these elements except 0. Okay, so for some A2, for some A1, I can get some AI such that AI equals to A1. For A2, I will get some AJ such that A into AJ equals to A2. This is like this. Okay. I'm erasing this portion. Okay. I'm erasing the middle part portion. So now this is a ring with unity. This is a ring with unity, commutative ring with unity. That's why 1 belongs to there. This is multiplicative unity. This is 1 belongs to there. So by this one, there exists some AR belongs to R such that A into AR equals to 1. Okay. Equals to AR into A, because this is a commutative ring. So it means, what does it imply? It implies that A is a unit. I have taken that A is not divisor of 0 and I have proved that A is a unit. So my first option is correct. Any non-zero element in R is either unit or divisor of 0. So option B, that is wrong because it's a negation of A. Okay. Now for the third one, see, every prime ideal is a maximal ideal. Now you should know that if you work with finite commutative ring with unity, on that set, on that ring, any prime ideal is always maximal ideal. Generally, in a commutative ring with unity, maximal ideals are prime ideals, but in a finite commutative ring with unity, all prime ideals are also maximal ideals. So that's why the option C is also correct. Now go to the fourth option. It has been said that if R has no zero divisor, then order of any additive subgroup of R is a prime power. Okay. So now if R is has no divisor of 0 and it is a commutative ring with unity, then what does it mean? It is an integral domain, is it not? So R is an integral domain and it has been told that it is finite. So a finite integral domain is always field. So in that case, R becomes field. Okay. Now R is a field and it is a finite field. So a finite field is its order is always in the form p to the power n, where p is a prime. It look like order of a finite field. Okay. Then the field is always a group with respect to addition. Okay. And that's why the subgroup, its subgroup is always of the form p to the power r for some r. Okay. So that's why the subgroup of this R with respect to addition has the order of prime power. Okay. So that's why option D is also correct. So it's option A, option C and option D. These three are the correct options. To watch more videos like this, please subscribe, stay tuned, like and share. Thank you.